Hello and welcome to this video 4.1. This is the final section of the P7 course and it's all to do with stars, and in today's video I'm going to be looking at two questions to do with stars. The first is how hot and the second is made from what. So starting off, the most important thing to say at this stage is that this really is all to do with analysing the light from stars, and by looking at the light that is given out by distant stars we can tell how hot they are, and we can actually tell something about what they are made from, and it's all just to do with looking at light and actually extracting that information from light. It seems pretty crazy to begin with that you can tell that much, you can get that much information just from the light, but I'm going to go through and explain that, and yeah, we're going to work out how those things come to pass. So first up here, I've just got a quick picture. I've discussed this before earlier in the topic. These are images taken of our sun by NASA using a telescope that they call a SOHO. I can't remember exactly what it stands for, Solar Observatory of the Heliosphere or something like that. But these are four different images taken using different parts of the infrared spectrum, and they can see different details. There's certain features which appear more prominently with different frequencies, with different wavelengths, and this one in the middle is an image taken using the visible part of the spectrum. The reason I'm showing you this picture is just to remind us that stars are giving out radiation across the entire frequency. It's not just they give out one single colour or one single part of light, they're giving out a whole range of frequencies, and that's part of the reason that we like to use mirrors rather than lenses, so that we can observe the whole range of frequencies given out by these different stars. Now this picture here, I'm just showing you a piece of metal that's been heated up by a blacksmith, and as you can see, this metal is one material. It's just the whole thing is made of iron, but there's different parts of it are at different temperatures, and I'm sure if I was to ask you to guess which would be the hottest and the coolest bits, well, look, this bit's cool. This will still be probably too hot to pick up by hand, but it's this part here appears as its normal colour, a sort of blackish grey sort of colour. This is the red hot part of the material, and up here it's so hot that it is white hot. And this image serves to show that the temperature of an object affects the colour of it, or really, what is colour anyway? The temperature affects the light emitted, and since the light emitted, well, that's actually the wavelength of the light, or the frequency of the light, the temperature of an object, we get the wavelength of the light emitted changes. It varies with temperature, and this is a similar phenomenon to what we notice with stars. This image here shows a graph which has got the sort of typical intensity of radiation given out by a star, and what it shows is that, well, here on the y-axis here we're measuring the intensity of radiation of each frequency. So what this is showing is that this, for a particular star, basically how much light, how much radiation is being given out at different intensities. So in this part of the spectrum here, this corresponds to infrared, so we've got a relatively small amount of infrared light being given out. It's giving out a fair bit of light at the visible part of the red end of the spectrum. It's giving out more yellow light. It's giving out even more blue and ultraviolet light. Up here it's giving out a small ultraviolet, so this is, sorry, the blue region, the violet region. Then above the ultraviolet region here it's giving out no light whatsoever. But this is a typical curve that shows the different frequencies of different amounts of light given out by the star. Now notice this, one thing to point out here is that this, on the x-axis here, we've actually got, this is high frequency ultraviolet and low frequency here. So one thing to remember of this is that actually the frequency is decreasing down to this, or sorry, the frequency is increasing down to the lower part of the x-axis here. And this is a typical curve for what you might see for a star. And what we've been able to work out, or what astronomers have been able to work out by linking the colours and the temperatures, is this. This is the typical shape that we see for different stars, but there is a variance in this that depends on what the temperature of that star is. So for low temperature stars, and this is a star of about 3,500 Kelvin, it's got a fairly low output across the entire range of frequencies, and here we'd find the peak frequency, the maximum frequency. For a hotter star, we get a higher frequency as the maximum. For yet a hotter star, the frequency is increasing. Even hotter, increased frequency, even hotter, increased frequency. So this chart shows that as the temperature of a star increases, the peak frequency also increases. Similarly, for a hotter star, can you see that the area underneath the curve for our hotter stars is much greater than the area beneath one of these smaller, or not smaller, sorry, cooler stars? So under the hottest star, it's got a much larger area. That means it's giving out more radiation across all of the wavelengths. So hotter stars are putting out more energy. So hotter stars have got greater luminosity, that's what we say. Greater luminosity. Or they give out more energy. Every second. Okay, so these two features. For hotter stars, they give out higher frequency, more high frequency radiation, and also higher amounts of energy overall. Now you might remember from earlier in the course when we were talking about working out how far away stars were, it's quite important for us to know the luminosity, and then we can work out how bright is it and do comparisons with that. This is a good way of finding out. If we measure the range of frequencies given out and we find that most of it is given out and this frequency, we can do some analysis, find out the luminosity, and use that then in our calculations of distance and brightness, and that this all sort of comes in together, another way for us to analyze these stars. Okay, so the next question is, how do we go from just looking up in the sky and seeing a star to being able to work out how much of each frequency? Because obviously if you or I look at a star, it looks like it's just one colour, and to the naked eye it does look like it's one colour. This is where we need to draw back in on an idea that we encountered much earlier in the course, of producing a spectrum from a star. Spectrum. So if you shine in your light that appears to be white from the star, we can split it up using a prism and we can get the spectrum, and then we can split this up. I mean, this picture here just shows the visible regions, but we could also measure here the infrared regions and the ultraviolet regions, and from that work out which is the most intense. We can do it using a prism. The other way was using a diffraction grating. Light from our source, I mean, here it's got a picture of a Bunsen burner, this could easily be a star. We shine it through our diffraction grating, it splits it up, and we get a nice spectrum. So this is why this spectrum is important. Let me spell that again for you, that looks a bit messy. Spectrum. And what we call a device that produces a spectrum is a spectrometer. So this is useful to us. We're using a spectrometer, splitting up the light from the stars, and we can then work out which frequencies are coming through the most. And that can be used to then work out the temperature of that star. Not only can it be used, this is to work out how hot. Next up, we're going to look at from what. And to begin with, I've got here, so here we go, we're going to do the from what section. To begin with here, I've got some images of a sample of sodium that's being burnt in a blue Bunsen burner flame, and a sample of potassium that's being burnt in a Bunsen burner flame. And this is something you've probably seen in secondary school lessons and might have been, or definitely would have encountered in chemistry. This is what we call a flame test. And this picture shows the results of burning these two different elements in the same conditions. And in one case, the sodium produces a very yellow flame, and in the other, potassium produces a sort of lilac flame. Now this is similar with all different elements. They have characteristic colours, and when you burn them in an open flame, they produce those characteristic colours. And if we were to look at the light that was being produced from these and pass them through a spectrometer, now this is down here I've got what we'd call an emission spectra for sodium. So this is the one for sodium, and this is the emission spectra, or emission spectrum, sorry, because there's only one. Spectrum is singular. So this is the emission spectrum for sodium, and what it shows is if you put that light and you refracted it or diffracted it through a grating, you only come out with wavelengths at an extremely specific value. So the value of the wavelength here, so somewhere between 550 and 600, somewhere around about the 575 nanometer wavelength. And there's two very characteristic wavelengths here, and there is no light given out across the entire rest of the spectrum. If we did the same for potassium, we'd find something different, and this line here would be in the more purpley lilac region, which would be actually be a shorter wavelength, higher frequency, shorter wavelength. And we find this with all different types of elements. Here is an emission spectrum for hydrogen, and if you burn hydrogen in an open flame and put the light through a spectrometer, you produce this spectrum, and it has very specific wavelengths that correspond to that element. Now all different elements produce very different looking spectrums. So what we've got here is a tool that links the element, and it produces a characteristic emission spectrum. Now to use this, and for astronomers to use this, we need to understand what's going on here, and it involves looking at energy levels for electrons. It's been shown, and we've found out, that inside an atom, electrons can only exist in certain energy levels. There are set energy levels that they can exist in, and sometimes an electron will fall from a higher energy level down to a lower energy level, and when it does so, it loses a very specific amount of energy. The amount of energy lost corresponds with the difference in between these energy levels, and when it loses that energy by falling from a high energy level to a low energy level, it emits a photon. What's a photon? A photon is a little packet of light. So it's a packet of light energy. And this, the amount of energy this photon has, is specific to the energy levels, and that is specific to the element. So different elements produce different photons. Those photons have different amount of energies, and that results in us getting a characteristic spectrum. How is this useful to astronomers? Well, in stars, we're going to be having the elements inside here are going to be producing, so this is sort of a picture of the surface of a star, the elements are going to be producing light across loads of different wavelengths. But then that light has to then pass through the atmosphere of the star. And in the same way that specific wavelengths can get produced by a certain element, specific wavelengths also get absorbed by certain elements. And light that is travelling through this atmosphere will get absorbed if it's of the same wavelength as the elements inside this atmosphere. This diagram here shows the absorption. We're getting a load of particles. These photons are all travelling through the gas, and these ones here, these particles, their energy does not correspond to this material, to this element, so they pass straight on through. But here we've got a photon whose energy, the photon energy of this particular particle, corresponds exactly with the element that is passing through, and it ends up becoming absorbed. When it gets absorbed, it gives its energy to an electron, and that electron moves up to a higher energy level. And the result is that this photon carries on travelling through, all these photons carry on travelling through, but we don't get any of these photons through to the other side. They just don't make it through. So when we look at a star and we analyse its light, we then see an absorption spectrum. If we look at our sun, and analyse the light from it, what we notice is that even after we've passed it through our spectrometer, there are certain missing wavelengths. We see these black lines on our spectrum from a star, and that is because this wavelength has been absorbed by the gases surrounding that star. And this particular wavelength, it means that there must be hydrogen in that atmosphere surrounding the star. This wavelength here again is characteristic of hydrogen, and if we look across our spectrum and we spot all the points here and can match them up with known emission spectra for known elements that we've got here on Earth, we can work out what is inside the atmosphere of a star. As a final point, I'd just like to remind you of this slide that I showed you in a previous video when we were talking about redshift. These three diagrams here are all absorption spectra. They show what light has been absorbed by the atmosphere of different stars. And each of them have got these characteristic lines which correspond with hydrogen. However, when stars are moving away from us, the result is, because of their movement, that the wavelength gets shifted. The amount that they are shifted corresponds with the speed of that star. So even though the distances between these lines is a constant, and we can use it to tell that it's hydrogen, we see this shifting towards the red end of the spectrum because they're moving away from us.
Now it's time for our wrap-up. Let's give it everything we've got. Ready? Begin.
So, to summarize what we've seen today, we can analyze light from stars, and by doing so we can work out how hot that star is, and we can work out what the star is made from. Stars produce light of all different wavelengths and all different frequencies, but what's handy to us is that we have worked out that the peak frequency and the amount of luminosity of that light depends on its temperature. So we have taken lots and lots of measurements of lots of different stars, and by looking at what is the peak radiation that it gives out, if it's got a high frequency for its peak radiation, that tells us it's a hotter star than something that has a low peak frequency. Also, if you look at the amount of radiation that's being given out across the entire spectrum, that corresponds to its temperature. Higher temperature stars give out more radiation across the entire spectrum. Secondly, we can tell what a star is made from by looking at the spectra produced from that star. this is by, well, there's a link between the emission spectrum, that is the specific wavelengths that are given out by a certain element. Here, when an electron loses some energy, it gives out a photon of a very specific wavelength. The same thing, that same specific wavelength will only be absorbed by an electron or by an atom, by an element, if it has those very specific energy levels. So what ends up happening inside the sun or inside the star, we're getting stuff produced across the entire spectrum, but it only gets reabsorbed in the outer atmosphere if those photons have got very specific energies. What that results in is an absorption spectrum. We look at the spectrum and we can see this line is missing, this line is missing, this line is missing. That means that the atmosphere of that sun, of that star, definitely contains hydrogen. This is just an example for hydrogen, but as with sodium and potassium and a whole range of elements that we've got here on planet Earth, we can look at all of these different ones and we can say this star must contain this much of this element, it must contain that much of that element, and we can then paint a picture of what's going on inside that star. What is its atmosphere made from? So just to put these into words for us as well, how hot? We look at the peak frequency and we look at the luminosity, and those two together tell us what the temperature is. And then from what we look at the, I was going to write the wrong one there, I was going to write emission spectra, but it's not the emission spectra, it is the absorb with a P, the absorption spectra of stars. By looking at those absorption spectra, we can tell what the atmosphere of a star is made from. Because those lines, the lines on the spectrum that are missing, if they're missing from that spectrum, it means that that element is definitely present in the atmosphere of that star. And that brings us to the end of stars, how hot, and made from what.